All right. Welcome, everyone. I hope you can hear me okay. Can you hear me fine?
Sounds good to me.
Okay, great. Yeah, this is the tutorial on tools for floating point debugging and analysis, FPChecker and FLiT. I'm Ignacio Laguna from Lawrence Livermore National Laboratory, and this has been prepared in collaboration with Ganesh Gopalakrishnan, John Jacobson, and Kaiden Lon from University of Utah. So we will present two tools, FPChecker and FLiT, that can help debuggers, can help developers in debugging debugging numerical problems, floating point problems. It doesn't necessarily, these tools won't necessarily address all the numerical issues we see, but they help in a large number of problems. So let me actually, I'm trying to set here my Zoom window correctly. Okay, so let's begin. So let's begin with some background on the numerical issues that we want to address with these tools. So porting is crucial, right? So we do a lot of, we spend a lot of time porting code. Every number of years we get new machines. We're going to get exascale computing machines here, and porting is crucial. And porting can take a lot of time, and it can be very challenging sometimes. In particular, one of the challenges porting is getting numerical consistency or numerical reproducibility, right? So in addition to be able to run applications at larger scales, maybe with larger workloads in new machines, we also want to make sure we reproduce the numerical results and we get reliable and reproducible numbers in the applications we run. And this can be a problem sometimes. This is challenging because there are several factors that, when you have an application that is not giving you the right a numerical answer, there are so many things that can be affecting the application and can be affecting the numerical consistency of scientific simulations. Some of the factors that can affect numerical consistency are the following. So number one, we're dealing with floating point, right? And so there is this floating point error pretty much everywhere, right? In the applications, libraries, at pretty much every layer of the software stack we have. Whenever we're using floating point, we might have error. And so we have to deal with that. It could be also that, okay, we're running the application now in a new hardware, maybe the GPU, and this GPU is implementing the floating point standard in a different way compared to how it's implemented in the CPU, right? So that could be another factor. And in fact, that's what happens. NVIDIA GPUs, they tend to implement most of the standard, but there are some deviations of it that we'll see later about that. It could be that you're running on a new compiler your code, and now you're getting a different result. Well, in fact, if you're running on a GPU machine, you will be probably using one compiler for the device code, MVCC, for example, and you may be using another compiler for the host code, right? So this, running your code in a new compiler could create problems of numerical reproducibility. You may be using optimizations that are aggressive, right? And you may be using fast math and things like that can complicate the reproducibility. And so the tools that we're going to present, FPChecker and FLiT, can help you in debug some of these numerical inconsistencies that you see. Let me give you a quick overview of these two tools, and then we'll get into the details of the two of them. So FPChecker is a tool that allows you to detect the floating point anomalies and exceptions. So, for example, you can detect none, infinity, subnormal numbers, issues like cancellation and things like that. Some of these anomalies emerge when the code is optimized. So it's good to have a tool that tells you where in the code this is happening, and so you have an idea of how you could potentially fix the code when this is happening. This FPChecker tool gives you a report, and it's an HTML report, and I'll show you later in the tutorial how you can see how this report looks like. And it supports most of the programming models we use, MPI, OpenMP, CUDA, and things like that. So we're going to go in the tutorial first with FPChecker, and then we'll move into the other tool, which is FLiT. So FLiT detects numerical inconsistencies that arise with compiler optimizations. It can locate the root cause files and functions that when these functions and files are associated with a particular optimization level, and you see inconsistencies, you can isolate where the problem is coming from and potentially change that function and maybe use a different optimization level for that function, and then your problem could be solved. Right now it supports CPU compilers, GCC, Clang, and others, and there is current work to support NVIDIA GPUs compilers. So with this introduction, let's get into the FPChecker tool. So later in the tutorial, I will give you a chance to run the tools. I will provide, so we'll provide a set of AWS instances that already have the software installed, and you can run some applications there, and I'll guide you through that. But first, let's talk about what the tool does, and then I'll give you details into how to connect into the AWS machines and things like that. So the way we use FPChecker is as a sanity checking tool. So it's good to run this tool to make sure you don't have floating point computations that are you don't have exceptions in your that are hidden in your code, things like non-infinity and such anomalies. You don't have them hidden in your program, and you know where they are happening. And the way we like to use this tool is it's the same way you use a spell checker. It could be that you're really good at writing, but sometimes often your spell checker can catch things that you didn't see. And so this is the way we like to sell this tool, is that you can run it and it will tell you potential pitfalls that you have in your code, right? Same way you use a spell checker. And so it detects, as I said, floating point exceptions. These are the floating point exceptions that are defined in the IEEE standard. So we have underflow that produce infinity values, overflow that produce infinity. We have underflows that can produce 0 or subnormal numbers. We could have divisions by 0 that produce infinity as well, and invalid operations that produce non or not a number. There's another exception in the standard defined as inexact, which basically happens when you have rounding in your code, but rounding occurs everywhere in every scientific application. So we don't really have to worry about rounding. So FPChecker will detect the first 4 and somewhat anomalies that I will show you later. I just wanted to give you an overview of the exceptions that we have in the floating point standard. So here's an example of the report. This is just a part of the report. Basically, it lists some of these anomalies and how many times they happen in the code. We have the infinity, non-division by 0. We have also subnormal numbers, underflows, and some other things. So let me give you an example of one of these anomalies that I find interesting in terms of reproducibility, and that is underflow. Or subnormal, actually generation of subnormal numbers. So underflow can become either subnormal or 0. But let me give you an example of how this could potentially be a problem in reproducing your results in different systems. Right. So for those of you who don't know what a subnormal number is, it's basically a small number that is it's allowed in the floating point standard, very small quantity. So for example, for double precision, it could be something like 1 to the power of minus 309 in this case. Those computations are fine, they are representable. The problem is when you combine those computations in optimizations. Right, we all want to use compiler optimizations. That could create a problem sometimes. So this is an example here where we have a division. We have X getting a result of a division, and then let's say your program will take a branch based on that division, the result of that division, either branch 1 or branch 2. So in one system, let's say in this system we have x86, and we're compiling with Clang GCC and optimization -03 and fast math. This will take branch 1. Now in another system with IBM Power 9, if you're using a different compiler, in this case, XLC, which is the vendor compiler for IBM, using a similar optimization level, -03, the code might take a different branch if you have a subnormal. And the reason for this is that the compiler optimization will optimize the division by a reciprocal operation. So it will be a times 1 divided by b, and that will produce an n in the division because you have a subnormal number. And so that will make your code take a different branch, right? So you could have a situation where your code is computing something and will produce different results on different systems for the cases of subnormal number. And this is why it's important to know where these computations are happening in your code, especially when you have high optimization levels. So here is an example of a report of this tool. And let me give you more details of what is reporting here. The first 4 cases are the most critical ones. And typically they should be unresolved quickly, right? So infinity, positive and negative, NaN, and division by 0. Then we have medium level, medium severity cases like underflow and comparison. So comparison occurs when 2 floating point numbers are compared for equality. And this sometimes could lead to inaccuracies. I mean, usually it's not recommended to compare 2 floating point numbers for equality. This will tell you where this is happening in your code, and you can go and check and say, okay, yeah, this is fine. I know what I'm doing here, no problems with that, right? Cancellation is another thing we can report here. Cancellation occurs when 2 nearly equal numbers are subtracted, and then you get a bunch of unassigned digits or garbage digits that don't mean anything, right? So this is very frequent in scientific computing codes. Most code will have cancellation for sure. And it's very tricky to eliminate. Most of the time it's very difficult to eliminate unless you change the algorithm, and sometimes that's impossible. But at least the tool will tell you, hey, you have cancellation in these lines, pay attention to that. And then the last 3 are essentially latent cases, which means that we are getting either very large computations or very small computations, and they are latent in the sense that they could become infinity or they could become underflow if you have a larger input. And so just pay attention to those cases. The tool is designed for HPC. So we support most of the programming languages we use, C, C++, CUDA, MPI, OpenMP, Raja, kernels. We can analyze code in the CPU. It's based on the clang LLVM tool for the CPU case, and for the GPU NVIDIA applications, we have a front end that also parses the kernel and instruments the code. So you have to compile with clang, right? So that's for C, C++ codes running on the CPU. You need to be able to compile with clang, and I'm going to show you an example later where we do that. For CUDA, you should be able to compile everything with NVCC. There's a slowdown, of course. This checking doesn't come for free. Here's a comparison of the slowdown for a number of proxy applications. And we compare it with Valgrind, which is a tool that a lot of people use, just so you have an idea of the slowdown that you would see. It's definitely slower than, I mean, it's faster than Valgrind. Slowdown is not that high, but well, you still need to take into account that you may not be able to run larger inputs with this, because there's definitely a slowdown. One last thing here, it's very easy to use. I'm going to show you an example later. Essentially, if you're compiling with Clang, all you have to do is to run FPChecker make, and it should be able to automatically intercept all the compilation commands, and it will instrument your code. And then once the code is instrumented, you can just run it. We also have wrappers for Clang and MPI. If you prefer to change your makefile, instead of running FPChecker make, you can modify your makefile and add those wrappers in the makes system. One last slide before the demo. We do have a recent tool called BeanFPI that performs binary instrumentation using the NVBit tool that NVIDIA provides. So for CUDA programs, this actually will be a better tool because we don't have to recompile the code. all you have to do is to preload a library and then run the code. And then it will detect exceptions in the GPU. And this is actually useful for Fortran OpenMP, where you're offloading the OpenMP into GPUs, and you can detect exceptions in the Fortran code. Using this, you don't have to recompile with Clang because it will be difficult for Fortran applications. However, we're not going to show this tool in the tutorial because the machines that we have right now don't have GPUs. So I'm going to show you the CPU version. But if you want to use it, it's available, and just you can contact us and we'll help you with that. Sorry. So now we're going to move into the FPChecker demo. So what we're going to do is that we have a number of instances prepared that already have the software installed. And I'm going to share with you a Google Doc, a Google Sheet, where you can get the IP address to connect to the system. If you want to run the experiments that we're going to be running, if you don't want to run, that's fine. Just look at what I'm going to be doing here. Let me stop sharing and let me share the Google Doc in the chat. And of course, if you have any question, I can also take it, but let me copy here the link. Here it is. So if you go there, you should be able to see a list of IP addresses and users. And so if you put your name in one of them and you plan to run the experiments, which are fairly simple, that would be great. If not, just look at the screen, and I'm going to replicate that in my screen. Let me share this desktop here. So we have this here. Okay. So you should be able to see that that list, and you can pick one of them and just do SSH and connect to them. Is there any question right now?
We need to put our own IP address there, or are we logging into a different IP address?
This is the IP address should be in the Google Sheet. Sorry, can you see my screen? Oh no, sorry, I'm sharing the wrong screen. To give me 1 minute here. I'm sharing desktop 1. Do you see the Google Sheet that I'm sharing right now?
I do see it, yes.
Okay.
Sorry.
So basically go to the link that I put in the chat, and if you plan to use one of these instances, just put your name there, and then you do SSH with the username provided, and the password is here. Is easy. Let me put the password also in the chat. Chat. Okay, so hopefully a few people can log in, and then you can run the experiment. So okay, I hope you can see my screen, and you can see that I have a terminal and the slides. So we're gonna run 2 applications that are simple to use, Lulesh and AMG. These are easy applications to download and run in these systems. These are not large. I mean, the AWS machines are capable, but we are not supposed to run very large codes here. So these are 2 small applications that can be run very quickly. So let me show you how to do it for Lulesh. Assuming most of you, and actually let me connect to the system that I'm going to be using. I'm going to be using this IP address, and I'm going to use user 1 here. Good, perfect. Okay, so I'm in the system now, and we're just going to follow the steps that I am sharing here in the slides. I hope you can see the terminal fine on the slides. How do you see that? John, can you confirm this is showing fine?
Yeah, everything looks quite clear to me.
Okay, okay, perfect. Okay, so first thing is I'm gonna get the application. I'm sorry. So I'm just gonna copy this step. You can do the same with me. So copy Lulesh, then I'm gonna move to the directory, and I'm gonna modify the make file. Because we want to, so I'm gonna use BI here. We wanna make sure that we are compiling with Clang instead of GCC. And so the application is using here GCC. So we're gonna change this by Clang. So what I'm gonna do is I'm gonna create another line and then change GCC by Clang. Clang. Well, in this case, it's Clang++, because we're compiling C++ here. Right, so this is the first step that I'm showing here. And then the other line I need to change is the actual macro that is going to be using CXX. So in this case, it's using the MPI macro here. So I'm going to modify this line. I'm going to create another one. And I'm going to say, just use the serial version, because we're just going to run the serial version. So I'm going to change MPI CXX by SER CXX. So it's basically saying, okay, for this macro, we're going to be using this command Clang. Okay, so that's the only modification that I'm doing to this make file. Hopefully this makes sense, right? And now I'm just going to compile. I'm just going to run make. It should. This is right now I'm compiling without FPChecker just to make sure I can compile with Clang. Because as I said, the tool depends on Clang. So I'm just making sure my compilation system works with Clang, and it's fine. It produced some warnings, but it's okay. I'm just gonna make clean, and now I'm gonna instrument with FPChecker. And so all you have to do is FPChecker make, and what it will do is that it will intercept all the Clang commands in the make file, and it will automatically instrument the code. And you should see things like there are a few warnings which are okay, but you should see lines like this that says FPChecker instrumented 8. So it means instrumented 8 floating point operations in this file. Okay. So now I have my application compiled with FPChecker, and I'm going to run a very small case for Lulesh. This is running Lulesh with size 5. Minus P means I'm printing the output, and then minus I, just 10 iterations, no more than that, because I'm just showing you a very small case here. And it runs, and it produces now a trace directory, FPC logs, that has a JSON file with the traces that it got. You're not supposed to read this trace file. What we're going to do is we create a report, but it's just to show you that it got some traces from the analysis. And the way we create a report is with this command, FPC create report. And then minus T means we can assign a title to the report. So in this case, I'm just going to use Lulesh. You don't have to assign a title, but that's what I'm going to do here. So
there's a question, Ignacio. In fact, will anything change if you're using CMake?
No, with CMake is fine, because CMake will generate a make file. As long as you have a make, it's fine. Yeah, it should work with CMake as well. We do have tests, a lot of tests with CMake, and we are able to intercept that as well. So, okay, I created a report, and you can see the report in the directory FPC report. There's an index HTML. So I'm gonna try to open the report in from a browser from this machine, and I'm gonna use the Midori I install a browser here, Midori. You can use in your own system any browser you want, but let me see if I can actually open it and it's not too slow. It might be slow. If it's too slow, I'm sorry. If it's too slow, I will transfer the report to my machine. Let's see. Let's see, it's trying to open it. And if, oh, the other thing is that you should have connected via SSH with -X. Otherwise, you'll have to transfer the report to your machine. But I hope you can see the report now. Can you see it?
Yep, I can see it on your screen.
Okay. So what is reporting from this application is that we have 0 in pretty much all the cases, all the events that we monitor. There is 7 cases of NaN, so not a number. So we can click on this number 7. I'm gonna click there, and then that will take you to the location where the NaN is happening. Hopefully, yeah, here it is. And it's happening in one line. So you can see here the NaN report tells you the file and then the number of lines that are affected by this event. And if you click on the 1, it should tell you the line or show you some code with the line. Yeah, so in this case, the NaN is coming from a division. And we already checked this in Lulesh, and what happens is that this division happens in the final phase of the application where they are going to report the results. And in the beginning, the 2 numbers here are zero. Essentially, the apps div is 0 and the local domain E computed here. The numerator and denominator are both 0. And so this is why it produces a NaN, but it's a benign NaN. It's not really affecting the application itself. We already checked that. And then you can go back to the main report here. It goes back to the original report. There is cancellation as well, which you'll see happening in many applications. At least tells you where this is happening. Okay, so this is the Lulesh case. I can move to the AMG case, which is the other case we plan on showing, or I can take questions as well. Let's see how much we're doing in time. Is there any question? Let's see in the chat. Does anything change? Okay, I already answered the CMake question. Yeah, I don't want to take a lot of time because I think I'm consuming time from Ganesh's talk. But if we don't have any other question, the other case is similar. It's just an AMG application. We download the code and run FPChecker there and see the report. If we don't have any other question, I will switch to Ganesh then for the FLiT tool.
Thanks, Ignacio. And if others have questions from Ignacio's talk, meanwhile, please feel free to post it in the chat. So it's about 3:29 here in Salt Lake City. Hi, everyone. My presentation will be the second project, which in this presentation, which talks about yet another source of floating point vagaries and how users might be confounded by certain answers not agreeing with their intuition. And so the tool is the floating point litmus tester. That's how the name FLiT arose. We developed it over several years, and Ignacio was part of the main development, and other folks not listed here. For this presentation, I would say Mike Bentley was the main author. John Jacobson, who is present here, he has been tending to the tool. Caden has been working on a GPU implementation in progress. So if you cannot hear me or something is unclear, feel free to chat or put it in chat. So the main idea is that when we compile standard desktop applications, we expect the answers to come out the same pretty much. When we approach numerical codes, we often get answers that we can brush away, like 10 by 3 might become 3.3332, and then we still accept that and move on. But things get very serious when we deal with certain physics problems where the user is lucky. They might see that some physics invariants get violated, like the gas density getting negative and all that. So that might be a point at which one truly pays attention to why it happened, and then one needs tools at that point. And it might be also occurring at the same time as you get tremendous speed up. So unless you are paying attention, you may get carried away by speed and not by the correctness. So the goal of this exercise is to help us understand better which flags and which optimizations and which compilers are able to deliver acceptable answers. And here acceptable is according to the user. We had to define an acceptance test, which is part of the FLiT tool. And if the acceptance predicate says true, that means then you can shoot for the flag that gives you the maximum speed up. So that's the general nature of the tool. So long story short, it is a search tool that helps you understand where the results might go out of band and where speed ups may not be adequate, or you may get the best combination of both in some rare cases. So when you have a numerical issue, what is a feasible approach to investigate? Today's existing tools, which are more rigorous and formal, are simply unable to scale up and work with users, make files, and with a variety of compilers. So our objective in creating such a tool was to make it a simple bisection kind of a search tool, which takes users' code. There are some requirements on the user's code that it should not have run-to-run non-determinism, where it exhibits a different control path and exposes different codes. If you have a data raise or MPI wildcard received, this can easily happen, and the onus is on the user to fix that. And many codes are not non-deterministic like this, so one can enter the run FLiT test case and get ready to investigate further. So in your entire search space, you may find that all the answers are acceptable, in which case you don't need the further steps. And then, or you might find the reproducibility performance graph and find the best operating point. But if you really cannot go beyond a certain point, unless you use O0 or some very low level optimization, you clearly need to identify which file may contain a function that has numerical instability, and then perhaps rewrite it, or maybe just leave that file alone under low optimization, and the rest of the files can be compiled under higher optimization and then link it. There are these options available. So ideally, one likes to locate it to the source line. That is not quite possible with FLiT. So FLiT can take you up to the file containing the offending function. And in the more detailed version of feature set of FLiT, it can often take you to the function in that file. There is a follow-on work in Livermore called pliner between Livermore and UC Davis, which can often take you to the source line also. So this is the higher level setup for the tool. Determine the variability inducing compilations, analyze the trade-offs, locate the variability by identifying files and functions. So part of this tutorial will be presentation of the higher level ideas. And at some point, we'll be inviting you onto the Amazon instance where you can go to a specific directory. And luckily for us, there will be shell scripts waiting for you. You'll be simply typing in step 01 and then watch what happens, step 02, like that. And I'll try to move you along as to what these steps are doing. Okay. So the installation of FLiT itself has been made easy thanks to my students I mentioned. I will not go into how you get FLiT. It is available freely. And so assuming that you have gotten past the install, which in this case we have, the task of FLiT is to then populate a certain knowledge base. It's a TOML file containing the compilers that you have at your disposal and the flags you would like to apply. optimization, and the fast math flags. So once the files are populated, the TOML file is populated, FLiT can begin its search operation over that space. Okay, so it has handled large applications and several programs, and it needs a larger machine typically to run successfully. In these exercises, we have trimmed down the steps for fitting in within the format time. So we will take a linear algebra, a finite element library called MFEM, and we will thoroughly walk through many of the steps in terms of compiling it under different optimizations and seeing whether there is an optimization that violated the acceptance. Then there is the bisection phase where we will give you a teaser. And then the third is Lulish, which we will not provide any details. So at this point, assuming that you can still see my screen, I didn't see any comment otherwise, feel free to state. So let me bring up the terminal view at this point. So Ignacio and John, can you please tell me whether you can see my shell?
Yep, looks good.
Okay, and these slides have been diminished. So we will wait for folks to reach this point where they are able to go to their Amazon instance, and the directory should be used FLiT tutorial. Yeah. Is that happening to John or Ignacio? Can you go here?
I'm in here now. I'm not sure if anyone else is waiting, but
that's fine. Yeah. So this is where action begins. So we'll go to exercise 1, and now we can see what this exercise 1 is trying to do. Okay. And if you are not quite caught up and you want questions, so feel free to put it in the chat, and John can tell you how to get back to this point. Okay. Yeah. So we will select MFEM and then set up some, get a basic understanding of what this step is going to do. I had my cheat sheet down below, which I don't need to show. Okay. So first we are going to create the test we are going to run on this MFEM and investigate the reproducibility aspects of it. So the actual application itself has this many files and this many functions per file and this many lines of code, 100,000 lines. We will be trimming the search space down to 5 or 6 files so that it fits the time budget. Okay, so what does it take to create a test file? High-level idea. So let us see what this is about. Again, this is not 100% necessary to be done. Let's go to exercise 1, which I am, and then so if I do that, it will tell you that to actually create a testable version, there are some details such as we are going to redefine main to be MFEM main, things like that. This is to help run tests under FLiT's bisection control, even address the fact that it can be run under MPI. I'm not going to tell you the details. So these are documented. So there is a very simple test setup phase whereby you change the main function, and then it is ready to be compiled under different optimizations. Okay, so then we basically do FLiT update. At that point, it creates a makefile, and it auto-generates its own makefile, starting with your own makefile. So that way the users don't need to be worried that their makefile and all the make commands will be rendered obsolete. No, that will be incorporated into the FLiT testing suite. These are all features that makes the tool distinct and potentially very useful. Okay, so then we are going to create a search space. So like I said, there is a toml file. So let's look at the toml file. And there is one. The toml file tells you that it is prepared to search over G++ and these flags and clang. Okay, so roughly that is the goal. So make, run, build, will read that. And then it is creating the compilation search space and okay. So it's basically creating the search space by compiling. And so it is actually taking the various compilers and producing the C.O, as you can see. I could have done make minus b minus n, which I will show you. So just to tell you why it's taking some time, it is compiling, of course. We can use the J options and go higher in terms of parallelism. We are not doing that now. So let this finish. Okay, but the rest will be in terms of, so we can now see that it is compiling according to Clang's unsafe math and Clang with a fuse multiply. And it also creates a ground truth run. Ground truth run is, if I recall, G++ with O2. That is our baseline. So let us make minus BE minus N just to see what it had done. So this would give you, oops, that went too fast, so more. So what we did was, you see that? So it's taking each item in the toml file and compiling according to it. That's what we just did. Yeah. So right now we are here. So we are in exercise 1. We looked at how the make file was, the main program was modified. And we looked at the toml file, and then we built the different compiled binaries. Now it's time to do the bisection to see which compilation would break the acceptance test. So that would be in step 3. And it'll involve running a make run minus J1, but minus B minus N, yeah. Let's see what this does. This is what it would do. So it would actually be trying to run the different compilations and see which compilations compare favorably. So I'll now actually run it. So make run minus J1. So that would be carrying out the different compiled. So the results would be that it is actually running the fast math options and the FMA options for different compilers and populating the test database, which is in the results directory. Did I run the correct step here? Make run minus J1? Yes, I think I did. I may be off by 1 step. If I do that, let me know. But I think I'm saying the right things here. So it is creating the linked binaries, I think, where the different files were compiled under different optimizations, and it is creating the binaries. And now it's also running the ground truth run, and it is putting the results in the CSV. So I will have a brief picture later, but since it is taking some time, let me give you a visual of what was done. So FLiT bisection search is about taking a set of files and then compiling them under a baseline compilation and some selected files under higher optimization, and then producing a final executable linkage, linked image, which is then run to see whether it meets the acceptance test or not. And then we can do an exhaustive search, but we don't do that. We actually typically locate the compilation flag that jumped the baseline result and then bisect down towards it. So it becomes a logarithmic search at that point. I will not have the time to show how the search space is navigated and correctly pruned down. So bisection is the act of mixing different optimizations and then seeing whether that linkage produced a problem. The later step, which would not be possible to fit into the tutorial, would be once you find there is a file that violates a certain baseline acceptable results, it is a matter of locating which function within the file violates. So that part requires you to produce two different versions of the same file where each function is declared either as a strong symbol or a weak symbol. And at linkage time, we can select a weak symbol function here into the final assembly or the strong one. So we can produce even a what we call a Franken binary, which tells you, which allows you to mix different functions within a file, also situated at different optimizations. And this often works. Sometimes it violates the application binary ABI conventions and doesn't work. Okay, so that is the higher level overview of where this will go. But let us see where we are. We are actually at this point where we simply produced the different results, and the results directory will tell you the final effect of different runs under different optimizations. And there are these CSV files and the data files. The data files carry the performance information also. Okay, so we can now start viewing the set of results using the next step. So I ran the previous command directly, but I can do step 5 at this point, which is the SQLite. So more step 5 would tell you what I'm doing. I'm actually going to apply the SQLite commands to view the different compilations. So the current select command pulls out the first FLiT results. And so what is the next command? 6 would be to apply the right select commands to view a tabular form of what different compilations resulted in. So let us do that. Step 6. So it tells you at this point that the different compilers that we used under different flags, under basic optimizations and flags produced these outcomes in the compare function. The compare function of 0 means that things were acceptable in this case, and it is actually measuring the error, if I understand, the relative error, 0% relative error and 193% relative error. So for this compilation, G++703 under fuse multiply add, it gave a fair amount of speed, but the results were not acceptable. That is the situation we are. So then what do we do? So we need to now bisect. So the real facility at this point would be in exercise 3, which I would not look at. And that is an auto bisect. Auto bisect means I'm going to run a logarithmic search down and find the file causing the problem automatically for you. So in the interest of time, we are going to guide the bisect a little bit, noting that the problem happened under this compilation. So we are going to use that knowledge and feed it as a command line argument. So that's what we'll do. So like I said in the table, this means 193% relative error under G++. So we need to now see how to find which file was affected by that flag. So we only know which flag caused it, but we don't know which file. So we are in this directory, and let's look at the steps. The step 7 is the first one. So step 7 tells, again, is deliberately created for this tutorial to include the offending file just for expediency. We kind of cheat a little bit. We know this file will eventually have it, but the auto bisect would have located it for us. And we throw in a selected number of other files. We don't want to go through the 150 files. So let us do step 07. And then that tells you which sources will participate in the bisect. And then we do FLiT update. And the next command will do the FLiT bisect, which takes the particular makefile we just now created. And therein, we are going to guide it to say, to look for the particular flag causing a certain file to cause the result to change. So FLiT bisect. So all we need to do is step 9. So now it is actually trying to find out which file, when administered this optimization level, is changing the answer. And the expected result will be that at the end, we'll produce that this linear algebra dense math, the CPP, is the one. And it even gives you a little bit of a detail on which function, I think. So if we go to the last step, we would actually see the function. So it actually did a symbol bisect also in this shortened version. So you can see that it is creating different compilations and running it and checking for the score. And at this point, it has done the symbol bisection and found out that this function add mult AAT is the function within the dense math CPP that caused the result to change. So again, you would do an auto bisect to get to this point. We did not do that in the interest of time. So if you do step 10, it tells you basically the function within the file. So this is the function which does a simple looking linear algebra operation, and we haven't investigated as to why this function got ill conditioned. I hope this was an adequately pieced together with some gaps of an explanation. So roughly what we did is we selected an application. We had the user modify the main. We created a search option space using TOML. We let FLiT carry out that. And then we did an auto bisect. So in conclusion, I would say that FLiT and its bisection feature have been fairly useful for us in locating problems in several scientific codes. Some of them are applications, some of them are programs. And the way in which this work is benefiting the society is to guard science as we port tools to different machines and want to rely on the answers. So for further details, you may want to look at the features that I talked about in this article, and also even details such as these graphs can be, the information to produce such graphs can be obtained from FLiT, where every compilation is the x-axis under the TOML files, and the speedups you get from a baseline of G++O2, and all the blue dots are safe operating points. With that, I will turn the attention mic back to Ignacio and see if you have any questions.
Thank you, Anish. I think there is a question in the chat, and I believe John answered the question. I don't know if you want to take a look, but it looks like it was answered by John. Other than that, we're getting to the end of the hour. If there is any other question, we can take it now.
There was a question for Fortran. We haven't done Fortran at this point.
Okay. Yeah, there was a question on, I think that was on FPChecker.
What about Fortran? Oh, okay, okay. That
and
was
I answered that. Yeah.
Oh, okay, okay, right.
Yep.
Yeah, even for FLiT, some folks, some users request Fortran support. We'd be
There's
looking
another question now in the chat. Can you see the last one from Cameron?
Yes. Is there any way for users to add performance data into a FLiT shared database, which would be useful to share issues that we have? I think that's a good thing. We do generate the timing details. Yeah. Yes. We haven't done actual sharing of performance data.
I would say, I mean, there's nothing implemented on this front, but if there's a, like, if, I mean, you can run FLiT on any application that you're interested in testing, and it saves all of these results into a database automatically, and you're welcome to publish that for your own tool anytime you want. I guess is what I would say.
Yeah.
Okay. All right.
Thanks, everyone. We would love to rekindle interest in FLiT with the addition of hopefully the GPU bisector by the end of summer. And maybe even look for exceptions under FLiT compilation. These are all plans. And like I said before, there is a project called pliner, which is further investigating ways in which you can change the particular instructions in a file to see whether the problem goes away. So that Ignacio and Dr. Cindy Rubio Gonzalez are working on.
All right. Well, thank you everyone for attending the tutorial. If you have any questions, you can also send us an email. We're happy to answer. And otherwise, thank you for joining.
Thanks.